A planet can be there, circling a distant star, and you will never see it with your eyes. Not because it is too small to matter, but because starlight is loud, and planets are quiet. So we learn to listen for the faintest signatures, the tiniest repeats, the smallest dependable clues. A dip in brightness, a shift in colour, a wobble on the sky, a brief magnification, a speck beside a glare. This evening, we let those clues arrive slowly, one by one, until an unseen world becomes real enough to name. I'm Madeline Rowe, astrophysicist turned private eye, and tonight I'm on assignment as a planet hunter. Not the kind who chase footprints in mud, but the kind who chase patterns in starlight. On my desk is a thin folder, and inside it are the quietest clues in the universe. I set my pencil to the side and open the folder before taking a calm breath that settles the room. My desk lamp pulls a gentle circle of light over the cover page, which reads with a simple label, Exoplanet Detection. This evening, we'll be discussing a star that dims by a hair, a spectrum that shifts by a breath, a position on the sky that wobbles by a whisper. All things that, if we're patient enough and measure carefully, add up to worlds unknown. And if you like slow science stories like this, you can subscribe and come back for another case file whenever you need a quiet place to rest. Before we begin, it helps to remember what we are up against. A star is a brilliant sphere of plasma, radiating outward in every direction, flooding space with light and heat. A planet, by comparison, is a small body that reflects a tiny fraction of that light, and often emits only a faint glow of its own. From far away, most star systems collapse into a single point of light in our telescopes, like a distant porch lamp on a foggy road. So in most cases, detection is not about seeing the planet directly, but about measuring how the star behaves when the planet is there. That shift in mindset is the heart of this case file. We treat starlight as data, and we treat motion as a trace left behind. We measure brightness over time, and we look for repeated patterns that match the physics of an orbit. We split starlight into a spectrum, and we look for tiny Doppler shifts that match a star's back and forth motion. We measure positions on the sky with exquisite precision, and we look for a subtle, looping wobble around a centre of mass. There are a handful of primary methods, and each is like a different kind of instrument in a quiet investigation. Each one is sensitive to different sizes of planets, different orbital distances, and different kinds of stars. Each one carries its own biases and its own false alarms, and the best work happens when methods overlap, when one clue confirms another, and the picture becomes steadier. We will move slowly through them, with time to rest between ideas, letting the science stay clear and gentle. The first method is the one that has delivered an overwhelming share of known planets, the transit method. A transit happens when a planet passes in front of its star from our point of view and blocks a small portion of the light. If you record the star's brightness night after night, you can see a tiny, temporary dip, and if the orbit is steady, that dip repeats on a regular schedule. That schedule is a period, and a period is a fingerprint of orbital distance once you know the star's mass well enough to use Kepler's laws. In this way, a planet reveals itself as a rhythm in starlight. The transit signal has a simple geometric core that makes it feel almost peaceful in its clarity. The depth of the dip is roughly the area ratio between planet and star, which means it scales like the planet's radius squared divided by the star's radius squared. A bigger planet blocks more light, and a smaller star makes the same planet's shadow look deeper. The duration of the transit depends on how fast the planet is moving and the path it takes across the stellar disk. And the exact shape of the dip carries information too, softened by a real effect called limb darkening, where the star's edges look dimmer than its centre. In practice, transit detection is both elegant and demanding. You need photometry that is stable enough to notice dips that may be only hundreds of parts per million, sometimes less. You need careful treatment of noise from the instrument, from the detector, from pointing drift, and from changes in the space environment or Earth's atmosphere, depending on where the telescope sits. You also need to understand the star, because stars are not perfectly quiet light bulbs. They have spots, flares, granulation, pulsations, and long-term cycles that can look, at first glance, like planetary signals. So the transit method is not just a single dip, it is a whole workflow. Clean the light curve, remove trends, model stellar variability, search for periodic box-like shapes, and then test what you found. One classic search tool is called box least squares, and it does exactly what it sounds like, scanning across trial periods and looking for the best-fitting, repeating box-shaped drop in brightness. Modern pipelines often go further, using a blend of physical modelling and statistical learning to identify candidates and assess reliability. But the calm, central idea stays the same. A planet in front of a star makes a small, repeatable shadow. There is a quiet catch though, and it is purely geometric. A transit can only be seen if the orbit is aligned close to edge on from our viewpoint. That means most planetary systems will never transit for us, even if they are full of planets. So transits are powerful, but they are selective, and that selectivity shapes what we discover first. Short period planets transit more often, and their transits are easier to catch, simply because you see more repeats in a shorter time span. Another catch is that not every dip is a planet. A faint eclipsing binary star system in the background can mimic a transit if its light blends with the target star's light. A grazing stellar eclipse, where one star barely clips the other, can create a shallow, transit-like dip. Even instrumental artifacts can sometimes stack into patterns that look convincing until you examine them carefully. So transit surveys rely on follow-up and validation, using additional observations to rule out imposters and confirm that the signal truly comes from a planet-sized body. Some follow-up is straightforward and soothing in its logic. You look at the star at higher spatial resolution to see whether there is a nearby contaminant that could be responsible. You check whether the centroid of the light shifts slightly during the dip, which would hint that the dimming source is offset from the target star. You look for odd-even differences in successive events, which can betray an eclipsing binary with two different eclipse depths. And often you turn to another method entirely, one that measures motion rather than dimming, to see whether the star itself responds to an orbiting companion. That brings us to the radial velocity method, sometimes called the Doppler method. Here, the planet is not detected by blocking light, but by tugging on its star with gravity. A star and a planet both orbit a shared centre of mass, a barycenter, and the star's motion around that point causes its spectral lines to shift back and forth. When the star moves toward us, lines shift slightly to shorter wavelengths, and when it moves away, they shift slightly to longer wavelengths. The effect is tiny, but with stable spectrographs and careful calibration, it becomes measurable, and it becomes a repeating signature of an orbit. Radial velocity is a beautifully direct link between gravity and measurement. The amplitude of the star's velocity wobble depends on the planet's mass, the orbital period, and the inclination of the orbit to our line of sight. Because we do not usually know the inclination from radial velocity alone, the method yields a minimum mass, commonly written as m times sin I. If the orbit is close to edge on, sin I is near 1, and the minimum mass is close to the true mass. If the orbit is more face on, sin I is smaller, and the true mass can be larger than the minimum suggests. This is where the different methods begin to fit together like calm pieces of a puzzle. If a planet transits, you already know the orbit is close to edge on, which means sin I is near 1, and the radial velocity mass becomes much closer to the true mass. And if you know mass from radial velocity and radius from transits, you can compute density, and density tells you something fundamental about what the planet is made of. Rocky, icy, gaseous, or some mixture in between, with a spectrum of possibilities rather than a single label. In this way, two methods together do more than either one alone. Radial velocity, however, comes with its own quiet complications. The star is not still, and its surface is active, with spots and magnetic regions that rotate in and out of view. Those surface features can distort spectral lines and create apparent velocity shifts that have nothing to do with planets. Instrument stability matters as well, because you are looking for changes of meters per second, sometimes tens of centimeters per second, against a background of mechanical and thermal drift. So radial velocity work is as much about understanding noise as it is about measuring signal. The way astronomers handle this can be gently technical and still restful. They track activity indicators, such as emission in certain spectral lines, that correlate with magnetic behavior. They model correlated noise in time series, sometimes with Gaussian processes, which are a flexible way to describe variability that has structure rather than pure randomness. They design observing schedules that reduce aliasing and disentangle stellar rotation periods from orbital periods, and they treat each claimed planet as a hypothesis that must compete against alternatives in a statistical framework, where the simplest explanation is not assumed, but tested. A radial velocity signal also carries the shape of the orbit itself. A perfectly circular orbit produces a nearly sinusoidal velocity curve. An eccentric orbit produces a curve that is asymmetric, with sharper changes near periastron, where the planet moves faster. By fitting the curve, astronomers infer not only period and amplitude, but eccentricity and the orientation of the ellipse in space. These details matter because they tell you about the system's history, about interactions, migration, and dynamical stirring over long timescales. Now, as the case file continues, we move from dimming, and Doppler shifts to something even subtler, a star's position on the sky. This is astrometry, one of the oldest ideas in planet hunting, and one of the most challenging to execute well. If a planet tugs on a star, the star does not only move toward and away from us. It also traces a small orbit on the plane of the sky, a tiny ellipse or circle superimposed on the star's proper motion and parallax. If you can measure that sky plane wobble precisely enough, you can infer the planet's influence directly in angle, measured in arc seconds and fractions of arc seconds so small they feel almost unreal. Astrometry has a calm advantage that pairs beautifully with radial velocity. Because astrometry measures motion in the plane of the sky, it can constrain the inclination of the orbit. That means it can break the M-sin-I ambiguity and yield a true mass, not just a minimum. In systems where both radial velocity and astrometry are available, the two methods complement each other like two orthogonal views of the same dance. One sees the star's motion toward and away, and the other sees the star's motion sideways across the sky, and together they reconstruct the full orbit more completely. But astrometry is hard because the signals are so small. The size of the astrometric wobble depends on the planet's mass, the planet's orbital separation, the star's mass, and the distance to the system. A massive planet far from its star produces a larger wobble, and a nearby system produces a larger angular signal, simply because the same physical motion subtends a bigger angle when it is closer to you. So astrometry tends to be most sensitive to long-period massive planets around nearby stars, and it requires careful separation of the wobble from the star's own proper motion across the sky and the annual parallax caused by Earth's orbit around the Sun. If you let that settle, you can feel how much of astronomy is patient accounting. A star's observed position changes because Earth moves, because the star truly moves, and because it may be wobbling due to companions. A good astrometric model layers these effects: a parallax ellipse, a straight line drift, and a periodic orbital motion. Each layer has parameters, and each parameter must be fit with data that are precise, stable, and gathered over time. This is why long baselines matter, and why micro-arcs, second-class measurements are so valuable when you can get them. As the folder rests open on the desk, we can pause and notice a pattern across these methods. Transits are strongest when the orbit is aligned. Radial velocity is strongest when the planet is massive and close in. Astrometry is strongest when the planet is massive and farther out, and the system is nearby. Each method is a different slice through the same population of worlds, and each slice is biased in a different direction. So when you read a headline about a typical exoplanet, it is worth remembering that typical often means typical of what our methods can easily detect. The deeper truth comes from combining methods and correcting for what we miss. Now we turn another page in the case file, and the lighting on the desk stays soft and steady. The next method is gravitational microlensing, and it feels almost like a quiet coincidence turned into science. Microlensing occurs when a foreground star passes nearly in front of a background star from our perspective, and the foreground star's gravity bends and focuses the background light. The background star brightens temporarily, not because it changes, but because gravity acts like a lens. If the foreground star has a planet, the planet can add a short, distinct perturbation to the brightening curve, a small anomaly that hints at a companion mass in the lens system. Microlensing is gentle in its logic and dramatic in its timing. The events are transient, lasting days to weeks for the main brightening, and sometimes only hours to days for the planetary deviation. The alignment that produces a strong event is rare, and the same event does not repeat on human timescales. So microlensing is a survey game, watching dense fields of stars, often toward the galactic bulge, and waiting for gravity to do its brief, predictable work. When it happens, the light curve becomes a record of geometry, mass ratios, and relative motion projected onto the sky. One calm way to think about microlensing is to picture the light curve as a smooth hill. A single lens star produces a characteristic rise and fall in brightness, a symmetric shape in the simplest cases. A planet adds a ripple on that hill, a bump or dip that appears when the background light path skims a region of high magnification called a caustic. The timing and shape of that ripple constrain the planet-to-star mass ratio and the projected separation in units related to the Einstein radius, which is the natural scale set by lens mass and geometry. It is a method that can detect planets far from their stars, including cold planets that would not easily show strong transits or radial velocity signals within short observing windows. Microlensing also has a quiet limitation that is worth letting sink in slowly. Because the events do not repeat, follow-up confirmation is different from the usual approach. You cannot simply wait for the next transit or the next orbit to see the same pattern again. Instead, you rely on the internal consistency of the light curve, on modelling, on parallax effects when they can be measured, and on additional constraints from high-resolution imaging years later, when the lens and source stars have moved apart enough to separate. It is a method that rewards patience across years, even though the signal itself flashes by in days. The next page in the case file is direct imaging, and it is the method that most resembles what people casually picture when they think of seeing an exoplanet. But direct imaging is not simple sight. It is an advanced struggle with contrast and optics, a careful attempt to subtract a star's overwhelming glare so a much fainter companion can be detected nearby. The star can be millions to billions of times brighter than the planet in visible light, and the planet sits at a tiny angular separation, close to the star's diffraction pattern and instrumental speckles. So direct imaging is a discipline of controlling light, shaping it, blocking it, and then processing what remains with great care. A typical direct imaging system uses adaptive optics to correct for atmospheric turbulence when observing from the ground. It uses a coronagraph to block the star's core and reduce the amount of starlight reaching the detector. And it uses post-processing methods that exploit how speckles behave with wavelength or field rotation, allowing residual starlight patterns to be modelled and subtracted. The planet appears as a point source that moves with the star across epochs, distinguishing it from background objects and noise. This method is most sensitive to young, massive planets on wide orbits, because young giant planets are still warm from formation and glow more brightly in the infrared, and wide orbits give larger separations on the sky. Direct imaging is not only about detection, though. It can also deliver spectra, and spectra can reveal atmospheric chemistry, clouds, temperature structure, and surface gravity indicators in some cases. A faint spectrum spread out in wavelength becomes a kind of fingerprint of molecules and conditions. In this sense, direct imaging can jump ahead in the story, taking you from "there is a planet" to "here is what its atmosphere seems to contain," at least for the brighter and more favourable targets. It is a method that asks for technological excellence and then rewards it with rich physical detail. Now, as the desk lamp hums softly, we can bring our attention back to the methods that tie detection to characterization most directly. When you can measure both mass and radius, you can compute bulk density. And density is one of the most informative first steps in understanding a planet's nature. A high density suggests a composition rich in rock and metal, while a lower density can point to substantial volatile layers, thick atmospheres, or hydrogen and helium envelopes. But density is not a full answer, because different internal structures can sometimes yield similar bulk densities, especially when you have uncertainties in mass and radius. So we treat density as a constraint, not a verdict, and we keep gathering clues. Transits offer another gift: transmission spectroscopy. During a transit, a small fraction of the starlight passes through the planet's atmosphere, if it has one, before reaching us. Molecules and aerosols in that atmosphere can absorb or scatter light at specific wavelengths, causing the effective transit depth to vary with wavelength. By measuring how the transit looks in different colours, we infer hints of atmospheric composition and structure, such as water vapour, sodium, potassium, or hazes, depending on the planet and the data quality. The signal is subtle because it depends on the atmospheric scale height, which in turn depends on temperature, mean molecular weight, and surface gravity, and those dependencies are part of why the method feels like careful, layered reasoning. There is also eclipse spectroscopy, sometimes called secondary eclipse observations. If a planet passes behind its star, the combined light from star plus planet drops slightly when the planet's contribution disappears. In the infrared, that drop can measure the planet's thermal emission, and in visible wavelengths, it can sometimes measure reflected light. From the wavelength dependence of the eclipse depth, you can infer brightness temperatures and constraints on atmospheric composition, again within a modelling framework that respects uncertainties. And as a planet moves around its star, you can sometimes measure phase curves, gentle variations in brightness that trace how the planet's day side and night side contribute as the viewing geometry changes, offering a window into heat redistribution and winds at a broad level. These characterization techniques are not always available for every planet. They demand high signal-to-noise data, stable instruments, and often repeated observations. They also demand careful stellar characterization, because the star's spectrum and variability are the baseline against which the planet's subtle contribution is measured. In some cases, stellar spots can imprint features that mimic atmospheric signals, especially if the star's surface changes between observations. So a calm, rigorous approach always keeps the star in the story, not as a backdrop, but as an active participant in what we measure. At this point, the case file has introduced multiple ways planets can leave traces. Now we can slow down and look at what makes a detection credible, in a way that feels like careful, methodical detective work rather than excitement. In science, a detection is not only a signal that looks right, but a signal that survives attempts to break it. So astronomers test robustness. Does the signal persist across different data reductions, different detrending approaches, different model assumptions, and different subsets of the data? They ask whether the signal correlates with known systematics, such as spacecraft pointing, temperature, air mass, or changes in background light. They also use injection and recovery tests in many surveys. You take the actual data, inject synthetic planet signals with known parameters, and see whether the pipeline recovers them reliably. This measures completeness, which is the probability of detecting a planet of a given size and period in that dataset. Completeness, together with the number of stars observed, allows you to infer occurrence rates, correcting for the fact that you do not detect every planet that exists. This is one of the quiet triumphs of exoplanet science, turning an imperfect, biased set of detections into a statistical picture of how common different kinds of worlds are. There is another calm concept that sits behind many detection claims: the difference between detection and validation. In some cases, you can confirm a planet dynamically by measuring its gravitational influence, such as a radial velocity signal that matches a transit, or transit timing variations that show planets interacting with each other in a multi-planet system. In other cases, especially for small planets where radial velocity confirmation is difficult, researchers use statistical validation, calculating how likely it is that the signal could come from various false positive scenarios compared to a planet scenario. This uses population models, follow-up imaging constraints, and the shape of the transit itself, and it yields a probabilistic statement, not a dramatic proclamation. In a quiet way, that is exactly what science is comfortable with. Quantified confidence rather than absolute certainty. Now, let us drift gently back to the transit method for a moment and explore one of its deeper, softer details: timing. If a planet's orbit were perfectly isolated, every transit would occur exactly on schedule, like a metronome. But in multi-planet systems, planets tug on each other, and that can cause transit timing variations, where the transits arrive early or late by minutes, sometimes more. Those timing shifts are not noise. If they are coherent and modelled correctly, they are information, and they can reveal additional planets, planetary masses, and orbital resonances. It is another way gravity writes its story into light, not as a dip, but as a subtle change in when the dip happens. Transit durations can vary too, in a smaller way, if orbital inclination changes over time due to interactions or precession. And in rare cases, the shape of the transit can be affected by star spots crossing events, where the planet passes over a darker region on the stellar surface and the light curve briefly brightens relative to the expected dip. Those features can be used to infer stellar rotation and spot distributions, and even the alignment between the planet's orbit and the star's rotation axis through a related spectroscopic effect called the Rossiter-McLaughlin effect, where the planet blocks part of a rotating stellar disk and distorts line profiles during transit. The point is not to memorize terms, but to feel the richness of the measurements and how many layers of physics sit inside a simple statement like, "The star dimmed." And when we let that richness unfold slowly, it becomes soothing rather than overwhelming. Radial velocity, too, has a quiet depth beyond the basic wobble. A planet's signal can be blended with others in a multi-planet system, producing a sum of periodic motions that must be disentangled. Sampling matters because the times you observe can create aliases, false periods introduced by cadence, seasons, and day-night cycles for ground-based work. So astronomers often use periodograms to identify candidate periods, then refine fits with full models that include multiple planets and noise terms. They might compare models using Bayesian evidence or information criteria, not as a ritual, but as a way to guard against overfitting, where the model starts to explain noise instead of signal. When you step back, you can see that all of these methods depend on a quiet partnership between physics and statistics. Physics tells you what a planet could plausibly do to a star's light or motion. Statistics tells you how confident you should be that the pattern you see is not a coincidence or an artifact. Neither is sufficient alone, and neither needs to be loud. They work best when they are patient, precise, and honest about uncertainty. Now we return again to astrometry, because it holds an especially calm promise for the future of planet characterization. A true mass matters, because it changes the physical interpretation of radius, density, and atmospheric scale height. Two planets could have the same radius and the same measured emsin I from radial velocity, but different inclinations, and therefore different true masses, and therefore different densities and compositions. Astrometry helps resolve that ambiguity by measuring inclination, and in doing so, it tightens the story from a range of possibilities to a narrower set of physically consistent worlds. This is why combining methods is not only satisfying, but scientifically essential, especially when the goal is to understand planets as physical objects rather than points on a plot. There is also a gentle conceptual link between astrometry and direct imaging. Direct imaging benefits from knowing when and where a planet should appear relative to its star, and astrometric orbits can provide that prediction. Likewise, direct imaging can confirm that a faint point is bound to the star by tracking common proper motion and orbital motion across time. In that sense, astrometry can guide imaging, and imaging can support astrometry, and the two together can map wide orbit companions with greater confidence. It is another example of how, in astronomy, different instruments are not rivals, but collaborators in a shared investigation. Now, let the next part of the case file feel especially slow and gentle, because it is about biases, and biases are not mistakes, they are features of how we observe. The transit method is biased toward short-period planets and systems aligned edge-on. Radial velocity is biased toward massive planets and close-in orbits, though precision improvements push towards smaller masses over time. Direct imaging is biased toward young, hot planets at wide separations. Microlensing is biased toward planets at separations comparable to the Einstein radius and towards certain lens geometries, and it often probes populations far away in the galaxy rather than just nearby stars. These biases matter when you ask a big, calming question like, how common are planets? If you only count detections, you will undercount what you cannot detect, and you will overrepresent what your method favours. So surveys build completeness maps and detection efficiency curves, and then they use those to infer underlying distributions in planet radius, period, and sometimes eccentricity and multiplicity. This is where the field becomes quietly statistical, and where large datasets become not just collections of worlds, but measurements of populations. It is a kind of cosmic census, done with partial sight and careful correction. In a calm way, this is also where the star returns to the centre of the story again. To infer a planet's radius from a transit, you need the star's radius, because the transit depth gives a ratio, not an absolute size. To infer a planet's mass from radial velocity, you need the star's mass, because the barycentric motion depends on both bodies. So stellar characterization is not optional, it is foundational. Astronomers use spectra, stellar models, asteroseismology in some cases, and parallax distances to constrain stellar properties, and those uncertainties flow directly into planetary properties. That flow of uncertainty is another part of the gentle discipline of the field. A measured transit depth has an uncertainty. A stellar radius estimate has an uncertainty. When you propagate those uncertainties, the planet's radius has an uncertainty too, and the same is true for mass and density. Rather than hiding this, good work presents it openly, because the uncertainty is part of what the data truly say, and pretending otherwise does not make the planet more real. Now, as the user rests, we can let our attention drift to a quieter corner of modern practice: automation and machine learning. When surveys monitor hundreds of thousands or millions of stars, human inspection alone becomes impractical, especially for initial candidate identification. So pipelines incorporate automated vetting, sometimes using convolutional neural networks to classify light curve shapes, separate likely transits from likely false positives, and prioritize targets for follow-up. This does not replace physics, and it does not replace validation, but it can reduce the burden by filtering vast data streams into manageable sets of candidates. A responsible approach always tests these models carefully using labeled datasets, cross-validation, and injection recovery experiments, because a classifier that looks accurate on paper can still fail in subtle ways when faced with real, messy survey data. One gentle way to keep machine learning bounded to hard science is to treat it as an assistant for pattern recognition, not as a substitute for interpretation. A model can say, "This looks transit-like," But physics must still say, does this correspond to a physically plausible planet orbiting this star? A model can help detrend, but you must check that the detrending does not remove real transits or create artificial ones. A model can rank candidates, but you still need to assess false positive probabilities, check for contamination, and follow up where possible. In a calm pipeline, the machine helps you look, and the scientist decides what the looking means. Now, let us return to a deeper, slower treatment of transits, because they are a beautiful gateway into how measurement becomes physical inference. A transit is not only a depth, it is also a geometry problem. The impact parameter describes how centrally the planet crosses the star, and it affects duration and shape. Limb darkening shapes the ingress and egress, the gentle slopes at the start and end of the dip, and those slopes help constrain the chord the planet takes across the stellar disk. From transit shape and timing, you can infer orbital inclination, and with multiple transiting planets, you can infer whether the system is relatively flat and aligned, or more dynamically stirred. A transit can also reveal rings or moons in rare, subtle cases, though such detections are challenging and require extraordinary care. Even without that, the transit method can uncover planets in compact systems, where multiple dips overlap and must be disentangled. It can reveal resonant chains, where periods fall into ratios like 3:2 or 4:3, hinting at migration histories in the protoplanetary disk. And it can reveal that small planets are common, even though they are harder to detect individually, because population analyses show strong occurrence once completeness is accounted for. It is a method that, through volume, has reshaped our sense of what a planetary system can look like. Now we can let the pencil on the desk rest and simply move to the next set of gentle concepts: temperature and distance. Once you know a planet's orbital period and the star's properties, you can estimate the amount of starlight the planet receives, sometimes called insolation. With assumptions about albedo and heat redistribution, you can estimate an equilibrium temperature, which is a first-order approximation, not a full climate model. These estimates help place planets in context, such as whether they are likely to be extremely hot, temperate, or cold, though the real conditions depend on atmospheres, rotation, composition, and many other factors we often do not know. Here again, the field remains calm by being explicit about what is measured, what is inferred, and what is merely suggested by simple models. Radial velocity offers its own additional details in the same spirit. As precision improves, radial velocity detects smaller planets, but the challenge of stellar noise grows because the star's intrinsic variability can be similar in amplitude to the signal of an Earth-mass planet in some regimes. So the field develops techniques like simultaneous photometry to track stellar spots, high cadence observing to average over oscillations, and spectral line-by-line analysis to separate activity-driven shifts from true Doppler motion. The goal is not to eliminate noise completely, because stars are physical objects, not ideal sources, but to model the star well enough that the gravitational trace of a planet stands out as distinct, coherent, and repeatable. In that effort, patience is a tool as valuable as any instrument. Astrometry, too, becomes especially meaningful when you consider long-period planets. A Jupiter-like orbit takes many years, and to map it well, you need data spanning a meaningful fraction of that period. This is why long-duration surveys are so valuable, and why combining datasets across missions and instruments can be powerful when done carefully and consistently. The orbital fit must separate wobble from proper motion and parallax, and that separation improves as the time baseline grows and the signal repeats enough to become unmistakable. In a calm way, this is a reminder that some discoveries are not accelerated by excitement, but by time itself. Microlensing provides an almost complementary window, often sampling planets that are otherwise difficult to detect. Because the method can detect planets at a few astronomical units and beyond, and because it can probe distant lens stars, it contributes to understanding planetary populations across the galaxy, not only in our local neighbourhood. The signals are subtle but sharp, and the field relies on coordinated survey networks that monitor star fields continuously, ensuring that when an anomaly appears, it is captured with enough time resolution to model reliably. The modelling often produces a set of solutions with degeneracies, and researchers report those carefully, exploring parameter space rather than selecting a single best value without context. It is another example of science being steady and transparent about what the data allow. Direct imaging brings us back to the art of measurement because it depends so heavily on controlling optics. The diffraction pattern of a telescope creates rings and spikes, and imperfections create speckles that can masquerade as planets. So the work becomes a combination of hardware and software, of stable wavefront control and clever subtraction. Over multiple epochs, a true companion should move in a way consistent with orbital motion, while background stars will show different apparent motion relative to the target star's proper motion. And once a companion is confirmed, spectroscopy and photometry in different bands constrain temperature, luminosity, and atmospheric features, often interpreted through models of planetary cooling and evolution that connect luminosity to age and mass, again with uncertainties stated openly. Now, in the middle of this case file, it can be helpful to rest on a short, simple summary, like a quiet refrain. A transit is a shadow. A radial velocity signal is a Doppler shift. Astrometry is a wobble on the sky. Microlensing is gravity's brief magnification. Direct imaging is the careful separation of a faint point from a bright glare. Each method is a different way of reading the same physical truth. Gravity binds systems, and motion leaves patterns that careful instruments can measure. And those patterns, when treated with patience, become worlds. Now we turn toward a gentle, important part of the story, how we avoid fooling ourselves. In exoplanet detection, false positives are not shameful. They are expected, because the signals are small and the universe is complex. So the field develops layers of checks that are almost ritualistic in their calm repetition. Does the signal repeat with consistent period and shape? Does it persist across different processing choices? Does it appear in independent datasets or instruments where systematics are different? Do alternative astrophysical scenarios explain it as well or better? For transits, one common check is whether the inferred companion size is plausible given the transit depth and the star's radius. A planet that would need to be larger than the star is a clear warning sign, and even less extreme cases can suggest a stellar companion rather than a planet. Another check is whether the transit depth changes with wavelength, which can indicate a blended eclipsing binary, because a stellar eclipse often has a stronger colour dependence than a planetary transit, though atmospheres can also create wavelength dependence in subtler ways, so the interpretation must be careful. High-resolution imaging can reveal nearby stars that dilute the light and alter the inferred planet radius, turning an apparently Earth-sized planet into a larger one once contamination is accounted for. These are not dramatic twists, they are slow corrections that make the final result more faithful to reality. For radial velocity, a key check is correlation with activity indicators. If the velocity signal tracks changes in spectral line shapes or chromospheric emission, it may be driven by stellar activity rather than a planet. Another check is stability across wavelength, because activity can produce chromatic effects, while true Doppler motion shifts all lines consistently, though instrumental effects must be considered too. Researchers may also test whether the signal remains when modelling known stellar rotation periods and their harmonics, or when excluding epochs affected by flares or instrumental anomalies. Again, the idea is not to be suspicious of every signal, but to be honest about how easily nature can mimic what we seek, and to respond with careful modelling rather than haste. Now, we can let ourselves drift into a slightly deeper layer of the mathematics without making it sharp or stressful. In detection, you often compare models: a model with no planet, a model with one planet, a model with two, and so on. Each model predicts what the data should look like, and you compute how well it matches, accounting for noise and uncertainties. A good model does not only fit the curve, it also leaves residuals that look like noise, rather than another hidden pattern. When residuals show structure, it can be a hint of additional planets, additional stellar variability, or unmodelled systematics, and the investigation continues. There is something restful about this, if you let it be. The universe does not demand that we be quick. It only demands that we be consistent. Repeatable patterns are the language it offers us, and careful measurement is how we learn to read. Now we return to characterization again, because it is where detection becomes a portrait rather than a dot. Consider a planet with a measured radius from transits and a measured mass from radial velocity or astrometry. The density suggests whether it is likely rocky or volatile rich, but there is a continuum with sub-Neptunes, mini-Neptunes, super-Earths, and planets with thick atmospheres that blur simple categories. Atmospheric measurements add another axis, because a planet's atmosphere can be hydrogen-rich, water-rich, CO2-rich, or cloud-dominated in ways that change the observed spectrum and the planet's thermal behaviour. When we infer atmospheric composition, we do so through retrieval models that compare synthetic spectra to observations, exploring parameter space and reporting posterior distributions rather than single-point answers. And this statistical honesty is part of what keeps the field grounded. Transmission spectra can be muted by clouds and hazes, flattening features that would otherwise stand out. This is not a failure, it is information, because clouds and hazes are physical phenomena with implications for atmospheric chemistry and dynamics. Secondary eclipse measurements can reveal temperature inversions or lack thereof, depending on how emission varies with wavelength, though these interpretations are subtle and depend on data quality and modelling choices. Phase curves can suggest whether heat is transported efficiently from day to night, offering coarse constraints on winds and circulation patterns in hot atmospheres. And even reflected light measurements, where possible, can constrain albedo, which depends on clouds, composition, and surface or atmospheric scattering, again with careful caveats. Now, let the case file take a slower turn toward the bigger landscape of exoplanet discovery history, without dwelling on dates or drama. The field began with detections that were easier, massive planets close to their stars, because those leave strong radial velocity signals. Then large transit surveys revealed that small planets are common, and that planetary systems can be compact and diverse. As precision improved, the variety expanded. Planets in multi-star systems, planets around small, cool stars, planets in resonant chains, planets with unusual densities, and worlds that do not fit the tidy categories we might have expected from our single example in the solar system. This diversity is not chaotic. It is structured, and the structure emerges through population studies that link planet occurrence to stellar mass, metallicity, and environment, slowly building a theory of formation and evolution anchored in data. A calm point worth keeping in mind is that detection is not a single moment. It is the endpoint of many decisions: how the data are calibrated, how trends are removed, how noise is modelled, how candidates are selected, how follow-up is prioritised, and how final confirmation or validation is performed. Different teams can sometimes reach slightly different conclusions on the margins, especially for weak signals, and that is normal in a field that lives near the limits of precision. Over time, as more data arrive and methods mature, the picture stabilizes, and the community converges on robust detections, while leaving uncertain cases in an honest category of candidate until evidence improves. This is not indecision, it is the steady self-correction of science. Now, as you rest, we can let the tone soften further while staying faithful to physics. Think of a star as a lighthouse whose beam is not a rotating sweep, but a constant radiance measured in precise numbers. A planet's orbit introduces a tiny modulation to that radiance, a small change in what reaches us, and our instruments, built by careful engineering, are sensitive enough to track it. The act of detection is not mystical, it is measurement plus model, repeated until the result is reliable. And the act of understanding is not hurried, it is the patient layering of constraints until the planet's properties become the most plausible explanation left standing. Let us take another quiet refrain, slightly expanded, just to settle the mind again. We see shadows in light curves, we hear motion in spectra, we trace tiny loops on the sky. We watch gravity bend light for a moment. We carve away glare to reveal a faint point. And then we combine these clues to turn detection into characterization, and characterization into a deeper understanding of how planetary systems form and change. Now we can drift into a gentle, methodical tour of what a modern transit pipeline might do, step by step, without rushing. First, it collects time series photometry, measuring flux in consistent apertures or using pixel-level methods to handle pointing drift. Second, it calibrates and detrends, removing instrumental signatures and long-term stellar trends while trying not to distort short transit-like features. Third, it searches for periodic signals, scanning period and phase space for repeating dips, and computing a detection statistic, like signal-to-noise, of the folded transit. Fourth, it performs diagnostic tests, checking for secondary eclipses, odd-even differences, centroid shifts, and other signs of false positives. Fifth, it fits transit models to estimate parameters like period, radius ratio, impact parameter, and duration, producing uncertainties via sampling methods. And then, for high-priority candidates, it schedules follow-up, spectroscopy for radial velocity, high-resolution imaging for contamination, and sometimes multicolour photometry for additional constraints. A modern radial velocity workflow has its own calm steps. It begins with high-resolution spectra taken with stable, temperature-controlled instruments, often with simultaneous calibration sources to track drift. It extracts velocities by measuring shifts in spectral line patterns, often using cross-correlation or forward modelling of the spectrum. It corrects for Earth's motion, because the observatory is moving, and that movement introduces large Doppler shifts that must be removed to see the tiny residual induced by a planet. It monitors activity indicators and line shape diagnostics, because the star's surface can create apparent shifts. It fits models that include one or more Keplerian signals plus noise models, comparing alternatives and reporting credible intervals for parameters. And when possible, it combines those results with transit or astrometric information to pin down inclination, true mass, and density with greater certainty. Now, let us slow down and make space for one more gentle theme: how planets can be missed, even when they exist. A planet might not transit because the orbital plane is tilted slightly away from our line of sight. A planet might be too small to produce a detectable dip in a noisy light curve, especially if the star is active or the data are sparse. A planet might be too light to produce a radial velocity amplitude above the stellar noise floor, even if the instrument is precise. A planet might be too old and cool to be bright enough for direct imaging, or too close to the star to be separated within the telescope's inner working angle. A microlensing event might not occur in the observed sample because alignment is a matter of chance and field coverage. So absence of evidence is not always evidence of absence, and population inference is the calm method by which we learn what is common even when we cannot see every instance. At this stage of the episode, the desk lamp feels warm and constant, and the case file feels complete enough to rest in your mind without effort. So we will spend a little time in a slower drift, revisiting each method in a more atmospheric way while staying true to the science. Not as a separate section, not as a new topic, but as a quiet walk back through the same corridor, noticing details you might have passed the first time. This second pass is often where understanding settles, because repetition, gentle and unforced, helps the brain relax into the concepts. And in a sleep story, that settling is part of the purpose. A transit, again, is a planet's shadow crossing a star. The star does not dim because it weakens, but because a small disk blocks a portion of its surface from our view. The periodicity ties the event to an orbit, and the depth ties the event to a size ratio. When we fold the light curve by the period, stacking many transits, noise averages down, and the shape becomes clearer, like a faint engraving emerging under a careful rubbing. And when we fit a physical model that includes limb darkening and geometry, we turn that engraving into parameters with uncertainties, a quantitative description of what the planet must be doing if it is truly there. A radial velocity signal, again, is the star's response to the planet's gravity. The star moves because the planet exists, not because we choose to model it that way, and the Doppler shift is how that motion reaches us through light. The amplitude is a clue to mass, and the phase is a clue to orbital timing, and the shape is a clue to eccentricity. But the star's surface is alive, and its activity can masquerade as motion, so we measure the star carefully, not only its velocity, but its line shapes, its chromospheric indicators, its photometric variability, and we build noise models that respect correlated behaviour. When the planet's signal remains after those tests, it feels less like a hopeful guess and more like a steady conclusion. Astrometry, again, is the star's tiny dance on the sky. The star drifts across the background as it moves through space, and it traces an annual parallax ellipse as Earth orbits the Sun, and on top of that, it may wobble due to companions. The wobble is small, but it is structured, repeating with the orbital period, and its orientation and amplitude encode inclination and mass influence. When that wobble is measured, it restores true masses, and true masses help every other inference become more physically grounded. And even when the wobble is near the limit of detection, the method remains a model of patience. Measure, separate layers, accumulate time, refine, and only then conclude. Microlensing, again, is gravity's brief lensing effect. A distant source star brightens because a foreground lens star passes near the line of sight, bending light in a way general relativity predicts. A planet around the lens introduces a short feature, a deviation that can be modelled in terms of mass ratio and geometry. The event does not repeat, which forces the field to be precise in the moment and patient in later confirmation methods that may come years afterward. It is a reminder that the universe sometimes offers its clues only once, and that careful observation can still make that single chance useful. Direct imaging, again, is the attempt to see the planet's own light, whether thermal emission or reflected starlight, by suppressing the star's glare. It is a triumph of optics and processing, and it is most successful for wide, young planets that glow more brightly and sit farther from the star in angle. It can deliver spectra and photometry that enrich the story quickly, offering atmospheric hints that transit methods might not access for non-transiting planets. And it still demands careful confirmation, because speckles can mimic planets, so multi-epoch motion and spectral consistency become key checks. When all that lines up, the faint point becomes a companion with a trajectory, and the case file gains a new kind of evidence, light from the planet itself. Now, the last pages of the folder focus on what it means to close a case file without overstating the conclusion. In astronomy, we learn to speak in probabilities and intervals. We learn to say what we measured directly and what we inferred by combining models and assumptions. We learn to state limitations, not as apologies, but as the boundaries of what the data can support. And we learn to keep the door open for revision when better data arrive, because the goal is not to be first, but to be right. That attitude is part of why exoplanet detection has progressed so quickly and so steadily. As instruments improved, the field did not simply announce more planets, it improved its ability to quantify uncertainty, to validate, to correct biases, and to build a population-level understanding that connects back to formation theory. The story is not only a catalogue of worlds, it is a measurement program that turns faint patterns into a coherent map of planetary architecture across the galaxy. And even when the details are complex, the underlying theme remains simple and calming. Gravity and light, measured carefully over time, can reveal what we cannot see directly. That is the quiet magic of hard science, and it is enough for tonight. Now, in the final minutes, I let the folder rest closed on the desk. The lamp's light remains soft, and the room remains still. The case file has done its work, and it does not ask you to hold onto every detail. It only invites you to remember that far away, around ordinary stars, there are ordinary gravitational dances, and that those dances leave measurable traces in starlight. A shadow, a shift, a wobble, a brief lensing brightening, a faint point beside a glare. And when those traces repeat quietly and reliably, we call them worlds. Good night.